in class today we were talking about a setup kind of like this, and I was talking about how you can put a ground reference. You know, you could put it here on the negative side, in which case the negative side is 0 volts, and then the top is positive 10 volts, and in this scheme this would be 6 volts, right? Similarly, I said, hey, you can put your ground on the other side. You can put it up here, making the positive side 0, which would make this negative 4, and then this would be negative 10 volts. Okay. The question I got that was a fun one was, what if you put the ground here in the middle of the two resistors? And my gut reaction was, ooh, that's a problem, that's ill-defined, but it actually isn't. And I want to walk you through how when I got up to my office, I actually reasoned through it. So what this problem is equivalent to is basically a situation here where you have a V plus terminal. And note that I'm being very careful not to specify a voltage yet, to ground that's pushing a current through the 4 ohm into the ground. And you've got a V minus terminal that has a 6 ohm resistor, and it's pulling current up from the ground. And this is the key thing. In fact, this ties into what I was talking to one of you about after class, is conservation of current still has to be observed. That's the key thing. So however many electrons this one is pushing into the ground, this one has to push that many electrons up, and the whole point of the power supply, this is the power supply here, it could be a battery, it could be whatever, is that it's going to take those electrons and move them back around. So it has to be the case that the current through this resistor and the current through this resistor have to be equal. But what is also true is that the difference between these terminals still has to add up to 10 volts. So we have two equations and two unknowns. We have that V plus minus V minus has to add up to 10 volts. And we have that V plus, I hope this works out, over 4, I wrote it on my paper upstairs, has to equal the negative of V minus over 6, okay? And so then when we work this out, we get that V minus equals negative 3 halves V plus. And so then if we do this difference, what we get is we get V plus minus 3, that should be 3 halves, 3 halves V plus, and that minus negative 3 halves V plus, so we get 5 halves V plus equals 10. And so V plus equals 4. So this terminal is 4 volts. And when you multiply this out, you get that V minus equals negative 6 volts. Now, one of the things that's cool about this setup is you'll see that because V equals, we have to have the same current, and V equals IR makes voltage drop proportional to the resistor value, that the positive voltage does happen to be exactly proportional to the resistor, and the negative voltage has to be equal to this resistor. And in fact, this relationship would be true even if this was 40 ohms and 60 ohms. This would be 4 volts and negative 6 volts. And the key thing is 4 minus negative 6 is 10. So by grounding here, what we're doing is we're maintaining that potential difference, that delta V of 10 remains, but what this point and this point are specifically is now pinned by this middle point, which we're saying this point has to be 0, and so we work the math out that this has to work out to negative 6 and this has to work out to positive 4. And that's how that problem works. Now, one other question that I got at the end of class that I think is useful to think about is sometimes, this is a separate problem, but I think it's a similar point. Sometimes you'll see a diagram that looks like this. I've got a 5 volt power supply, I've got a resistor, and then I'm going to ground, and this 5 volt is referenced to ground. This doesn't look like a complete circuit. What's going on? The way to understand the use of ground rather than batteries is the hydraulic analogy. Think of this as, so in a totally closed loop, you can think of it as a hydraulic system where the water is fully contained in the system. It goes through this tube and it comes back up this tube to the beginning. But you could also, in the hydraulic analogy, think of the ground as a lake. And I'm dumping water into the lake over here, but in order to keep the current going, the current return is I have to be pumping water out of the lake. And it doesn't have to be the same water. In the case of my iPhone, it's kind of I don't want to say the same electrons, but like, the electricity is following a closed loop, whereas when I have a scheme like this, what I'm doing is I'm dumping the electrons arbitrarily into the ground over here and pulling them out of the ground over there, but it's the same amount of electrons, so it's still a loop, and current has to be conserved over that whole loop. And it was thinking about that really helped me be like, oh, duh, this is a simple problem. All right, cool.